Okay, hello. Welcome to the last plenary talk of today. So it's my pleasure to introduce our speaker, Maria Chudnovsky from Princeton University in the United States, who will tell us about forbidden induced graphs and 3D compositions. So, yeah, you can start.
Okay, thank you very much. Thank you for inviting me. I truly wish I could be there in person. I cannot believe I'm missing out on such an amazing opportunity, but hopefully another time, hopefully in the near future. So you can see my screen, right? So what I'm going to talk about is work I've done with various people in the last roughly year and a half. And so different results here are joined with different colleagues, and I'll mention who did what. But the general topic is forbidden induced subgraphs and 3D compositions, and I'll explain what I mean. So I'm a graph theorist. I study graphs. Graphs have vertices and edges, and what I mostly focus on is structure of graphs with that have certain configurations forbidden. Now, what do I mean by forbidden configurations? That means you cannot delete vertices to reach a certain configuration, right? So things are forbidden under the operation of deleting vertices. And this is called forbidden under induced subgraphs. And now that I've given you the intuition, I'm going to say more precisely what that means. So we say that H is an induced subgraph of G if the vertex set of H is a subset of the vertex set of G. And then, right, so that's the point about deleting vertices. And then about edges, the rule is that if you have two edges, if you have two vertices that you kept, right, both X and Y are in V of H, and they were adjacent in the graph you started with, then they must remain an edge. Right? Obviously, you don't add edges, right? It's a containment relation, but also you're not allowed to delete edges except by deleting one of their ends. So let's see an example here. This is a graph. This is an induced subgraph of that, because to get this from that, you delete this vertex, and then you keep the other 5, and all the edges are there. This is not an induced subgraph of that, because right, they have the same vertex set. So to get this from that, I would somehow need to get rid of this edge, and that's not something I'm allowed to do. Right? Deleting edges is not an allowed operation. The most well-known graph containment relation is that of taking subgraphs, not induced subgraphs, but subgraphs. And then you're allowed to delete vertices however you like, and you're allowed to delete edges however you like. But that's not what we're doing here. Here, the only way to get rid of an edge is by deleting one of its ends, one or both of its ends. So I'll say H is an induced subgraph of G. I'll denote it like this. And now I'm going to slightly abuse notation. And if you're not a graph theorist or a logician, probably it won't bother you at all. So there's something, if I draw this graph twice, is it the same graph or is it two different graphs? So for me, it's the same graph, right? I don't label vertices. If I can find something here that looks like that, I don't care which vertices I deleted. So I'll say it precisely once for people who care. I will say that H is an induced subgraph of G when H is isomorphic to an induced subgraph of G. I will not, everything will be up to isomorphism. Okay, so now a family of graphs is hereditary if it's closed under taking induced subgraphs. Right? If for your family, if a graph is in it, then all its induced subgraphs are in it, you call this family hereditary. Okay. So what I'm interested in are hereditary families of graphs. So possibly the most well-known hereditary family is a family of perfect graphs. And let me tell you what those are. So we say a graph is perfect if for every induced subgraph, the chromatic number and the clique number are the same. What does that mean? The chromatic number of a graph is the following. Probably I don't need to say that, but I'll say it anyway. So you color the vertices, and there's only one rule that adjacent vertices should get different colors. And you want to do it with as few colors as possible. The smallest number of colors with which you can do it is called the chromatic number of the graph. Now, what's omega of h? That's the clique number. That's a little less well known. But what that is, so a clique in a graph is a set of pairwise adjacent vertices. And then omega of h, or the clique number of the graph, is the maximum number of pairwise adjacent vertices. Or in other words, the maximum size of the clique. So now if you think for a second about graph coloring, you understand that the chromatic number is always at least the clique number, because if I have a clique, I must color all those vertices with different colors. And sometimes there's equality. And when there's equality, it's interesting. It's unusual, it's special, it's interesting. Now here I'm saying even more. Not only is there equality in my graph, for a graph to be perfect, not only do these two parameters need to coincide, but they need to coincide for all induced subgraphs. So it's pretty strong. And this is a notion that was introduced by Claude Berge in 1961. So probably his main motivation was the fact that he noticed that this is a good way to say many theorems that were already known at that time. There were all kinds of theorems of Koenig that you could all phrase as this class, all graphs of this type are perfect, and all graphs of that type are perfect. So somehow it was a nice generalization of a lot of things that were already known. But then it turned out that these graphs have other nice properties. And somehow that's how you know that you've stumbled across something good. That's how you know that your definition is worthwhile, when you defined it for one reason, but then suddenly it's good in some other ways. So let's see what else is good about perfect graphs except for this remarkable property. So first of all, when Berge defined perfect graphs, he made a conjecture that a graph is perfect if and only if its complement is perfect. And that means, so taking complements means reversing all adjacencies. You start with a graph, and now if you had two vertices that were adjacent, you make them non-adjacent. If you had two vertices that were non-adjacent, you make them adjacent. Right? So that's taking complements. And then Berge made a conjecture that a graph is perfect if and only if its complement is perfect, which is really an amazing fact, right? I mean, why would that be true just from this definition? But first of all, Berge saw it, and second of all, it is true. It was proved by Lovas in 1972. But then Berge made another conjecture. Not then, I mean, back in 1961. Berge made another conjecture about perfect graphs, which is this fact. But let me decipher for you what this says. So Berge conjectured that a graph is perfect if and only if certain configurations certain graphs cannot occur in it as induced subgraphs. What graphs are those? So these are odd cycles of length at least 5, and these are complements of odd cycles of length at least 5. And it's not hard to convince yourselves that odd cycles and their complements, if they're of length at least 5, cannot be induced subgraphs of a perfect graph just because they violate this rule. And if you think about an odd cycle, the biggest number of pairwise adjacent vertices is 2, but you can't color it with 2 colors. If you go 1, 2, 1, 2, 1, 2, 1, 2, you'll get stuck. You need color 3. So it's clear that, and for this class it's still harder, but not hard. So it's clear that these and those do not cannot be present as induced subgraphs as induced subgraphs in a perfect graph. But the hard part of this theorem, or this conjecture, was to prove that if you don't contain this and you don't contain those, then your graph is perfect. And that was eventually done. This is joint work with Neil Robertson, Paul Seymour, Robin Thomas, and myself. We did it in the early 2000s. So this is, another very interesting thing about perfect graphs. That this property is in fact captured by the fact that there are only 2 minimal families of imperfect graphs, right? If you don't contain this and you don't contain those, then you're perfect. Then there was an application, not application, but a property which kind of came from a different direction, from an algorithmic direction. So there are various problems in graph algorithms that are known to be anti-complete for general graphs. And among them, one of the most famous ones probably is computing the click number. So then Groche, and Schreiber were able to prove that if your input is perfect, then computing click number can be done in polynomial time, right? So it's NP-complete for general graphs, but for perfect graphs, it can be done in polynomial time. So this again tells you that these are very special graphs. And for perfect graphs, this implies all kinds of other problems that can be solved. For example, the stability number, that's the largest number of pairwise non-adjacent vertices, or the weighted version of this. You can find the chromatic number, you can find an optimal coloring in polynomial time. So a lot of problems that are, well known to be hard for general graphs, suddenly you can do them efficiently in perfect graphs. So this is a kind of very nice family of induced subgraphs. I don't know if that's what popularized induced subgraphs. Certainly in my world it did, but possibly other people had different experiences. I just want to say something about this theorem. So it's a theorem, they proved it. But the way the proof goes, they start with a perfect graph, and they start with a perfect graph, and then they translate the problem of finding maximum click, finding the click number, into a semi-definite program. And then they use techniques from combinatorial optimization to solve the semi-definite program, in particular the ellipsoid method. So it is open to find an algorithm for doing that you can say in terms of the graph, right? That you don't need to translate and then do something completely different, but you can just see what's going on in terms of the graph. Now, one might think, you write the semi-definite program, you understand what it says in terms of the graph, and follow the run of the ellipsoid method, and that would give you an algorithm in terms of the graph. But somehow it doesn't work. It's too hard. Nobody can figure out what it is. So there's probably some other way to do it, something to do with understanding the structure of perfect graphs well enough so that you could do some kind of recursion and solve and find the click number. But that's open. So this is a theorem, but finding what's called the combinatorial algorithm, and there's not a definition for that, but Sophie Sperkel taught me it's an algorithm that doesn't use division, and I'm very happy with this definition. So can you solve this problem without using division? That's still open. And the reason I spent a few minutes talking about this is because it's one of my favorite problems, so I want people to hear about it. Okay, so this is perfect graphs. This is just some advertisement for the field of induced subgraphs. And what you were supposed to learn from that slide is that some hereditary families are very nice. So now this slide is a disappointing reality. Let us ask, do all hereditary families have nice properties? And the answer is not at all. So what do I mean by that? Well, let's try to find parallels to perfect graphs. In perfect graphs, we know that the click number and the chromatic number are the same. So let's ask for something much weaker. Can you bound the click number? Can you bound the chromatic number as a function of the click number? And the answer is no. It's even false for triangle-free graphs. So the graphs with no triangle, which means the largest click and then has size 2, and arbitrarily large chromatic numbers. So really, no hope. Then the next question is, well, maybe if you forbid some induced subgraphs, something nice happens algorithmically. Maybe you can always solve omega. You always solve for omega. Let's find max click if you forbid some induced subgraphs. But the answer is, again, in general, no. Even if you forbid this graph, which is 3 pairwise non-adjacent vertices, right? A stable set of size 3. So even in graphs with no 3 pairwise non-adjacent vertices, you can finding the click number is NP-complete. So really, there is no hope in general. There's one lovely conjecture that does say that graphs with forbidden induced subgraphs are different than general graphs. And that's the Erich-Heinon conjecture. And I was going to say something about it, but I don't think I'm going to get to it. But let me at least tell you the conjecture, because it's really very satisfying. So, and again, the point of this conjecture is to say, if you forbid an induced subgraph, which seems like a very local property, that has global ramifications on the graph. Something global changes in the behavior of the graph if you forbid a fixed induced subgraph. Right? So it's kind of a local global type of behavior. Okay, so here's the Aristotle conjecture. For every h, there exists an epsilon, so that if h is not an induced subgraph of G, then in G, either there's a very large clique or there's a very large stable set. And again, just to remind you, a stable set is a set of pairwise non-adjacent vertices, and alpha of G is the maximum size of a stable set, or in other words, maximum number of pairwise non-adjacent vertices. So the conjecture says, if for anything I forbid, there's an epsilon, so that in the graph with that h forbidden, either alpha or omega is at least the number of vertices to the epsilon. Now, you might ask, why do I keep saying this is huge? Well, the reason I say this is huge is because if you don't forbid anything, then the biggest clique in the stable and the biggest stable set could be as small as log the number of vertices. But as soon as you forbid something, the order of magnitude changes. It jumps from being logarithmic to being the number of vertices to some power. And so this is a very nice conjecture that tells you that there is something different if you forbid an induced subgraph, no matter what induced subgraph you forbid. Okay, so now some hereditary families are nice, some hereditary families are not nice. That opens the door to a lot of questions, all under the umbrella of which hereditary families are nice, which hereditary families have nice properties. And so there are many ways to kind of say what you mean by nice properties, but I'll focus on two things. I'll focus on structure, being able to say something about the structure of these graphs, and the existence of efficient algorithms. One topic I will not talk about, even though I and other people have worked on it, is what happens to the chromatic number of a graph if you forbid induced subgraphs. But that's a subject for another talk that I'm not giving now. So right now I'm just going to talk about structure and efficient algorithms. Okay, so now when it comes to structure and efficient algorithms, there's a classical tool in both areas, both in structural graph theory and in graph algorithms, which is called a tree decomposition. And I'll tell you what it is. It's not so important that you're comfortable with all the details of what it is, but I'll also tell you kind of the intuition with which to think about it. Okay, so on a very high level, a tree decomposition of a graph is an attempt to represent a graph by a tree. And somehow some tree decompositions are very simple and some tree decompositions are very complicated. And this complexity measures how close your graph is to being a tree. If your graph is a tree, it has a very simple tree decomposition. If your graph is a huge complete graph, so complete graph means a bunch of vertices all pairwise adjacent. So if your graph is a million vertex graph where every two vertices are adjacent, that only has very complicated tree decompositions, or very complex tree decompositions. So it's very far from being a tree. That's roughly what the tree decomposition does. So now let me tell you what it is really. So I have a graph G, and a tree decomposition for G consists of two things, two objects, T and X, where T is a tree. And what X does, it's a map that assigns to every vertex of the tree a subset of vertices of G. Right, so on imagine a tree, and then on every vertex of the tree, you hang a bag of vertices that come from the graph you're trying to represent. And there are only two rules, right? There are only two rules. The first rule is every edge of the graph that you're trying to represent needs to be captured in some bag. Right, so for every edge of G, there is a V in the tree, so that both X and Y are in the bag that corresponds to that V. And the second rule is that if I look at a vertex of G and I see where in the tree it appears, that set of vertices of the tree has to be connected, has to be a subtree. So I call it the support of X and T. So again, I look at the vertex of the graph I'm trying to represent. Its support in the tree is the vertices of the tree in whose bags it appears. This support needs to be a subtree of the tree. So only two rules. Let me just do a couple of examples, just because it's kind of a complicated definition if you're not used to it. So blue is the graph and pink is the tree decomposition. So I start with this graph. It has vertices 1, 2, 3, up to 6. Now I'm going to construct a tree decomposition of it using the same tree, right? This graph is a tree, so I'm going to use the same tree for a tree decomposition. And what I'll do is I'll say 3 is the root of this tree. And then for every vertex of the tree, there's a unique path to the root. So like from 1, I go this way, from 4, I go that way. So now I build a tree decomposition where for every vertex, I put in its bag that vertex plus its unique neighbor on its unique path to the root. So for example, for 1, its unique path to the root was 1, 2, 3. So 1's unique neighbor on this path is 2. So the bag that corresponds to this vertex is 1, 2. For 3, its unique path to the root is 3. It doesn't have any neighbors on this unique path. So the bag that corresponds to it is 3. And you can check that this is really a tree decomposition. And notice that I've managed to construct a tree decomposition of this tree by using bags of size 2. So then let's do this graph. And let me not explain to you how I constructed this tree decomposition, but you can check that it is a tree decomposition. I'm using this 4-vertex tree to represent this graph. And you can see that the bags here have size 3. And in fact, I can tell you that you cannot find a tree decomposition of this graph with bags of size 2, because this graph is further from being a tree than that graph, right? This is a tree, this is a cycle. So something happens. In a tree, you can do bags of size 2. Here, you need to use bags of size 3. Okay, so now let me summarize this. So given a tree decomposition, you define its width to be the size of the biggest bag minus 1. And then the tree width of a graph is the minimum over all tree decompositions of its width, right? So I don't care how big the tree is. All trees to me are equally simple. I don't mind taking a huge tree. But what I care about is making the bag small, not assigning too many vertices of G to the same vertex of T. And so G has small tree widths, means G is close to being a tree, and the particular tree width of trees is 1. Right, the way I constructed this tree decomposition, you could do it for any tree. And if G is not a tree, then its tree width is not 1. Okay, so if this is the first time you're hearing about this, then all you need to take away is that tree decomposition is a way to represent a graph using a tree, and there's a complexity measure called tree width, and the smaller the tree width, the closer the graph is to being a tree. So now why do I care? The reason I care is because bounded tree width is excellent for efficient algorithms. I mean, first of all, if you get used to this notion, it's a very good structural description of a graph. And for that, I think you don't really need to think about how big the bags are. You can say, my graph is very complicated, but the bags are much simpler. That's as graphs. Somehow they belong to a much simpler class of graphs. That's also an interesting notion that I don't think has been studied a lot, but I'm thinking about this a lot, and I'd like to popularize it. But also, if you have bounded tree widths, so bounded tree widths means all bags have bounded size, then you can use a technique called dynamic programming to construct efficient algorithms, to design efficient algorithms for all kinds of problems that are NP-complete in general, such as optimal coloring, maximum weight stable sets, and many others. Okay, so let's. So I mentioned this question of when can you get the 3D compositions where bags are big but simple, but I'm not going to talk about that now. What I'm going to talk about is the more classical spin on this question, and that is which hereditary families have bounded tree widths. Right? I look at the hereditary family and I ask, is there a bound on the tree width of all graphs in this family? And this is similar to a question that was answered in the graph minor theory. So graph minors is another containment relation on graphs, much more topological somehow than induced subgraphs. And there it's known exactly what you need to exclude as a minor in order to get bounded tree widths. And what's known there is that you need to exclude a big complete graph and a big wall. So a complete graph, again, it's a bunch of vertices, a bunch of pairwise adjacent vertices. A wall is this graph. I'm not going to tell you exactly what it is, but it's a cubic graph that looks like this. And so for minors, that's enough. If you forbid the big clique and this, then you're guaranteed to have bounded trivids. But for induced subgraphs, it's much more complicated because it's much harder to not contain a minor than to not contain an induced subgraph. And for minors is a much more global containment relation. It tells you a lot about a graph that it doesn't contain a certain minor. And it only tells you a little bit about the graph if it doesn't contain an induced subgraph. So it's a much more somehow complicated question. What do you need to exclude as an induced subgraph in order to get bounded trivids? So, but that's a question I want to think about. So from our intuition that comes from graph minors, we can list a few necessary graphs: a big clique, a big complete bipartite graph, a big wall. Now you can now start doing tricks to the big wall. You can subdivide all edges. And if you subdivide all edges, that that still gives you a graph of big trivids. But with minors, if I take this graph and I subdivide all its edges, then this graph itself is a minor of the graph with the subdivided edges. For induced subgraphs, it doesn't work that way. You can check it. So I have to list all subdivisions as forbidden induced subgraphs. Otherwise, I'm still in trouble. Here's another thing you can do. You can start with a subdivided wall, and you can take its line graph. So what's a line graph? That means I build a new graph where the vertices of the new graph are edges of the graph I started with, and two vertices are adjacent if the two edges share an end. Now, in this particular case, in a cubic graph, it's much easier. What you do is you replace every vertex of degree 3 by a triangle, right? So you start with this, you subdivide the edges however you like. You still have precisely the vertices are precisely the vertices are drawn are of degree 3. And now you replace each of them by a triangle, and that gives you another example with large trivids. So you have to exclude at least all of those. I'm not saying by any means that this is a complete list, but if you allow one of them, if you don't exclude one of them, then there's no chance, and your trivid is huge. So then you might hope that this is it, right? You know, it's not quite like graph minors. I added all kinds of extra bits. I added the complete bipartite graph. I allowed some subdivisions. I allowed to replace the vertex by a triangle. So one might briefly hope that this is a complete list, but the answer is no, because of a very sad theorem of Saint-Hilaire and Chudnovsky. So they proved that if you take the family of graphs, which is the following, it doesn't have K4, doesn't have 4 pairwise adjacent vertices, and it does not contain any even induced cycles. It doesn't contain, as an induced subgraph, any cycle with an even number of vertices. Then, so you take this family, and they prove that for every K, there's a graph in this family with trivids at least K. So this family does not have bounded trivids. No, for every K, you can find a member here that has trivids at most, that has trivids at least K. Why is it bad? Well, the reason it's bad is because if you look here, so no K4, this is satisfied. K22 is just another way to describe a cycle of length 4, so that's forbidden. And it's a little harder to see, but it's not hard if you know what you're looking for, to prove that a wall subdivision and a line graph of a wall subdivision contain induced cycles of even length. So what they took is a much more restricted family than just forbidding this, and that. And they could still prove that it doesn't have bounded trivids. So there's, you know, the complete list is much more complicated than what I showed you. And so that's what this says. So that means there are other abstractions. Okay, so that's the bad news, but now let's move on to something a little more positive. So what if we bound the maximum degree? What if I say graphs in this family, but also maximum degree at most delta. A degree is, so in my world, all graphs are simple. So the degree is how many edges come out of a vertex, so equivalently in this case to how many neighbors a vertex has. And so now I'm thinking about graphs with no induced event cycle and maximum degree at most delta. So then in particular, I won't have a big clique, right, because it's delta. So they conjectured, so let's look at this thing. Same thing, no even induced cycles and bounded degree. Well, then everything is different. Then it turns out that the two-its is bounded. That's a theorem from about a year and a half ago with my student Tara Shami and with Kristina Ushkovich. And so we proved that for every graph in this family, its two-its is bounded by function of delta. So graphs with max degree 3 have much smaller two-its than graphs with max degree 3,000. But still, as it's only only the two-its is bounded by something that only depends on delta. And I should say that this was conjectured in a paper by these authors as a reaction to this theorem, because in this theorem you can observe that in this construction graphs have vertices of arbitrarily large degree. So this group conjectured it, they proved it for max degree 3, and then we proved it for all delta. And then they also, so this group also conjectured that the abstractions that are kind of inspired by graph minors are enough if you in addition bound the degree. Now, if you kind of think about this for a minute, so let me just say what it says here. So max degree at most delta, no big complete graph, no big complete biplane graph, no subdivision of some wall, no line graph of subdivision of some wall implies bounded two-its. Now, if you think about this for a minute, I didn't need to list the first two terms, because if maximum degree is bounded, then you can't have a huge complete subgraph. You can't have a huge complete biplane subgraph. But I just wanted to put them down here to kind of make a parallel to the slide with the necessary abstractions. Okay, so they made this conjecture, and I don't know if I believe this conjecture. A lot of my recent work has been motivated by this conjecture, but I don't know if I think it's true. I'll show you several theorems that support it, and I can tell you that we had several candidates for a counterexample, but none of the candidates are counterexamples. So I cannot disprove this conjecture, but I give it a 50-50 shot. All right, but in this talk, all I'm going to show you is why I think this conjecture is true. It's what kind of things I can prove, or we can prove, that support this conjecture. But it's like it's one of those disclaimers. The results listed here do not contain the views of the author. So even though everything here is theorem supporting the conjecture, I don't know if it's true or false. I don't know if I believe that it's true or false. Okay, so let me show you the results, and then I'll try to say something quick about the proof method. I should show you some results, and I'll try to say something quick about the proof method. Okay, so there was this theorem that says even whole free graphs of bounded degree of bounded max degree have bounded two-its. Then here's something else. So this is I call it halfway step, but it's a smaller half. So the degree is bounded. I forbid the line graph of a subdivision of a wall. But remember, we said you don't need, if the degree is bounded, you don't really need to worry about cliques and complete biplane graphs. So let's put them aside. So then I forbid the line graph of a wall. But instead of forbidding a wall, I forbid something much simpler. I forbid a big subdivided claw, a long subdivided claw. So what does that mean? So a claw is just this graph. It's a vertex with 3 pairwise non-adjacent neighbors. Now, if you subdivide each edge t times, you get STTT. Right? So STTT is this where you subdivide every edge t times. So then in this notation, this is S111. This picture is S333. And of course, if you take a subdivided wall and you take a vertex kind of in the middle and you start working from it in 3 different directions, that's going to give you a long claw. So that's why it's halfway. It's the second abstraction is what it's supposed to be, but the first abstraction is something much simpler. So then it's a theorem with Stara Brishame, my other student, Jamil Debek, and Pavel Rajewski, that in this case, the truth is again bounded. Okay. So, okay. Now, and I should mention that Vadim Lozhin with his authors have a related theorem, but it's about something a little different because they exclude a finite set of graphs, and we exclude an infinite set of graphs. So let me not go into that now. Okay, so we have this theorem. So now maybe let me tell you a little bit about the proof. And yeah, let me tell you a little bit about the proof. So okay, let's start from the beginning. So a separation in the graph is just two subsets of vertices, so the x and y, so that there are no edges from x delete y to y delete x, right? So all the edges between these two sets have an end in the intersection. That's a separation. And the order of the separation is the size of the intersection, right? So complicated separations have very large intersections. Simple separations have very little intersections. The simplest separation is just two sets of vertices with no edges between them. And there's something that I call theory of separations that was developed by Robertson and Seymour. And what they did, they connected collections of separations to bounded trivials. Or I should say, they connected collections of separations to 3 decompositions. So what they proved is that if I give you a set of separations that are what they call non-crossing, and non-crossing means this, but I'm not going to go into enough detail that this definition exactly matters. Somehow non-crossing means they line up nicely in the graph. You can say in this separation, the left-hand side is smaller. The left-hand side of this separation is smaller than the left-hand side of that separation. So they're not like this, but they're like that. Sorry, so it doesn't exactly matter what it means, but somehow it's separations that line up nicely. If you take a collection of separations that all line up nicely, then you can get a 3 decomposition that's closely related to the separations. And the way it's related is, so what happens with 3 decomposition? If you delete an edge of your tree, that gives you a separation in the graph. So then they're able to get 3 decompositions where the separations that correspond to deleting edges of the tree are precisely the separations in your family. Okay, so the kind of upshot is, given a collection of non-crossing separations, you can get a nice 3 decomposition. So now in graphs with forbidden induced subgraphs, there are a lot of natural separations lying around. And let me focus on one of them. I'll call it a star cut set. So a star cut set means a cut set in a graph is a set deleting which makes the graph disconnected. And a star cut set is a cut set that has the vertex adjacent to everybody else in the cut set. Right? So in other words, if I take a vertex and some of its neighbors, and that disconnects the graph, deleting that disconnects the graph, that's called star cut set. And of course, you can think of it as a star separation, right? As it's drawn here. You take the left plus the cut set and call it X. You take the right plus the cut set and call it Y. And that's a star separation. And star separation is something that happens naturally in many hereditary families. So, okay, so we know there's a connection between separations and 3 decompositions. We know we have some separations that come up naturally in our class. So we know where to go. The problem is that these separations are in general very far from being non-crossing. If I look at all star cut sets in my graph, they can cross in very complicated ways. So I cannot use this approach directly. But what happens is, and maybe let me not tell you all the details of that, but what happens is that you get theorems like that. So let's think about graphs with no induced event cycle with max degree delta. You can prove that all important star separations can be partitioned into boundedly many non-crossing collections. Lambda and non-crossing is the same. So it's not true that they're all non-crossing like the Robertson-Seymour theorems want them to be, but it is true that you can partition them into boundedly many non-crossing collections. So let's think of it, instead of having dimension 1, it now has bounded dimension. That's not so bad, right? There's some hope there. And then the second theorem is that if there's no star separation, there's no star cut set, then the tree width is bounded as a function of max degree. So continuing this idea of dimension, when the dimension is 0, there are no star separations at all. We know the result. We know that the tree width is bounded. And then, in general, the dimension is not 0, but it's bounded as a function of max degree. So, okay, so that's nice. Now we can maybe try to do induction on this dimension, on this what we call separation dimension. Here we go, star separation dimension, the number of laminar collections that you need in this theorem. And it turns out that this idea works. You can do, instead, Robertson-Zimmer did it once, we can do it many times. So let's, and I should tell you that their theorem is deep and complicated. The applications that we need is very simple. Somehow the one-dimensional case of their theorem that we need is very, very simple. But I refer to the original theorem because that's what inspired it. Then we noticed that actually our situation is simpler, but that was the source. Okay, so let's see how that works. So I'm doing an induction and star dimensional separation. You can use, as I said, a very simple case of the Robertson-Zimmer theorem to say that if you look at one laminar collection, then your graph breaks apart in the following way. You have a central portion that we call a central bag with star dimension 1 smaller, and then you have little bits of the graph attaching to it in uncomplicated ways. So what does that mean? So this is the big part, but with lower dimension. These are all not very large. They contain at most constant proportion of the vertices of the graph. And the way, and there are no edges between these different DIs. And then the way each DI attaches in the center is by star cut set, so uncomplicated way. And then you can prove, so why is any of this helpful? Because of this theorem down the bottom. You can prove that if you have a graph that looks like this, then the tree width of this graph is bounded as a function of the tree width of that graph and the max degree and how small those bits are. As I said, each of these bits is at most a constant proportion of the graph. So C is this constant proportion of the graph. Then the tree width is bounded by that. So that's exactly the inductive step that we needed, right? If only I could do it for star dimension k minus 1, then I could do it for the whole graph. And we already know it for star dimension 0. Now notice the tree width goes up as the star dimension goes up, right? So in this induction, my bound gets larger and larger at every step. But I'm only going to make boundedly many steps. I'm only going to make as many steps as the dimension. And for that reason, it works. And in order to bound the dimension, it's very important that the degree is bounded. That's the main application of bounded degree to prove that the star separation, that the dimension is bounded. Okay, so that's kind of a rough sketch of the proof. And it turns out you can do more or less the same thing to prove. So that was, right, that was a summary of the proof of this theorem, that if you forbid induced even cycles, the tree width is bounded. The proof of this theorem works similarly, except instead of having star cut sets, you have cut sets that are centered at a bounded length claw. And let me not tell you the details of that, but somehow everything works the same, and you get the same picture again, exactly the same picture, except here the adhesions, the way the little bits attached to the central bag were star cut sets. In the other application, these bits will be a claw subdivided boundedly many times plus its neighbors, but it works the same way. What's a little different is the base case, right? For even whole free graphs, we have these theorems that said when the dimension is 0, then we already have, we already have a bound on the treewidths. What happens in the claw-free result is that when the dimension is 0, you get a claw-free graph, right? You just, so here's, you're meant to prove the base case. And the base case is you just have graphs that don't contain K13 is an induced subgraph, don't contain this is an induced subgraph, don't contain the line graph of a subdivided wall, and have bounded max degree. If only you could prove that those have bounded treewidths, you would be done. Now, this is, if you think about it, at first, this is a complicated question. But the thing is, we know a ton about claw-free graphs. Paul Seymour and I have a 500-page series of papers describing the structure of claw-free graphs. So you can dig into that paper, and actually you don't need to dig that deeply. You don't need to dig 500 pages deep, but you can use our understanding of the structure of claw-free graphs to prove that these have bounded treewidths. Maybe let me not say how, but it's not hard if you understand the structure. Okay, so I have maybe a little bit less than 5 minutes left. Let me just tell you briefly what else we can do. So yeah, what else we can do using this method, and what do I mean by using this method? So noticing that there's some natural separations that can be partitioned into boundedly many laminar collections, right? So you can define some notion of the dimension that depends on the kind of separation that you have, and then doing something with the fact that whatever problem you're thinking about, not whatever problem, but the problem you're thinking about, you can reduce to a central bag, which is one dimension small. That turns out to be a powerful technique. Let me just show you a few things we can prove using that technique. So first of all, with Dara Abrishami, Jamil Debek, and Pavel Chudnovsky, we can get an algorithmic application. We can prove that you can compute maximum weight independent set in graphs with no long subdivided closed bounded degree. Then this is a result, I'm not going to tell you exactly what it says, but this is a result related to my favorite problem of computing max click or max weight click in perfect graphs without using division. So we can make some progress on that. And this is still work in progress. I hope this is a building block for something much stronger. That's joint work with Tara Abrishami, Jamil Debek, and Kristina Vushkovich. Then the theorem we were very pleased with, and we really thought we were almost done proving the whole conjecture with Tara, Jamil, Sefer Hajabi, and Sophie Sperkel. So a caterpillar is this, right? Everything is subdivided as many times as you like. And a wall contains a caterpillar as an induced subgraph. So we could prove if instead of excluding a wall and line graph of a wall, you exclude a caterpillar and the line graph of a caterpillar, so a subdivided caterpillar and the line graph of a subdivided caterpillar, and bound the max degree, then the treewidth is bounded. This is somehow very nice and symmetric, right? The theorem about claws that I showed you is very asymmetric. This is very nice and symmetric, but unfortunately, that's almost as much as we can prove. There's one more step we can make, but I'm not going to explain it. And this is the last thing. So there was a question that I told you Sentieri and Trognon constructed graphs with no induced event cycles in this huge degree. They also constructed graphs with no theta and no triangle and huge treewidths. So a theta is a graph like this. It's 2 vertices and 3 induced paths between them. And so they found, and let me not talk about it, but somehow it's an important graph it's an important kind of graph in the theory of induced subgraphs. So they constructed a family of graphs that don't contain those and don't contain triangles and have arbitrarily large treewidths. And same deal in their construction, they had to use vertices of arbitrarily large degree. So then they asked, what happens if you bound the max degree? Is it the same magic as you get with event cycles? Is bounding max degree guarantees bounded treewidth? And the answer is yes, and actually something much weaker already guarantees bounded treewidths if you bound the max degree. And what this is, so this is what we call a T theta. A T theta means 2 vertices and 3 paths of length at least T between them. right? Not just any 3 paths, but 3 paths as long as you like. And then instead of excluding a triangle, we exclude what we call a T-pyramid. So it's a triangle and a vertex with 3 long paths to it, paths of length T, and the subdivision rule. Right? So this and that contain triangles, but in fact, right, I'm excluding something much larger than a triangle, which makes it a much stronger term. And you can prove, again, it's with this group, you can prove that you get bounded truths. And let me stop here. Thank you very much.
Okay, thank you. So I'll remind viewers you can ask questions and I can read them to Maria.
Thank you.
And maybe in the meantime, I will ask a question. So this conjecture that I think you were talking about the second half of your talk, how close is it, or in which sense could it be close to be an if and only if characterization of bounded tree width?
So for bounded degree, it's a characterization.
It would be a characterization.
Yeah. So for this conjecture tells you exactly what induced subgraphs to forbid to get bounded truths, assuming the max degree is bounded. But we're very far from understanding what you need to say if the degree is not bounded.
Okay, right. So I think there are no questions. I hope I'm looking in the right place.
It's late and everything was clear.
Há questões? Não há. Desculpa, eu não percebi se há ou se não há. Não há, okay. So there are no questions.
Very good.
Okay, so then I think we should stop here. Thank you very much, Maria, for a very nice talk.
Thank you very much. Thank you for inviting me. Bye-bye. Good night.
Thank you, everyone who's attending.